Sounds good. Continue.
Okay, so this is what I got. And then this is this.
Oh,
is
nice.
HTML.
Yeah,
I
cool.
did it. Doug was like, well, I don't know how to use Postman. And I was like, well, I don't know either. I know a little bit, but I don't know enough for this assignment. So we'll just go your route. But this is what we came up with so far. And this is how it turned out to be.
I mean, what you have there is totally a workable solution to the problem. Like, I would guess you probably want to add some CSS to make it look a little bit nicer, but that's up to you.
Yeah. No, I will. I just from here, I just don't know. Like, is this, if I was to make this look like yours looks, is it okay? Or do I need more content to it? Like, do you want the what
No.
what did
I
yours,
mean,
I forgot how what yours looks like.
I think mine's actually have it up here.
I don't know. You could probably try using some Bootstrap Exona since you've have some experience with that. Just a thought.
No, yeah, no, I definitely will use Bootstrap. What I'm saying is, what other content do you want on there? Like, what other information?
I left it very open-ended on purpose. You're welcome to put whatever information you like. What you have there already is fine.
Okay, cool. So you want, so for me, it would just be more of a CSS.
Yeah, the goal really is to just prove that you can get data from a server and render it in a page. It's not really as important what you're rendering, more that you're rendering something.
Okay, cool.
Yeah.
It does not look
what you have here looks great.
Perfect. Yay. That's awesome. Okay.
Nice
I
work.
will. Thank you. I'll continue to. I haven't completed a homework assignment number 11, which is pretty easy, but I'll do that now. Okay. Thank you.
Cool. Just so everyone knows, if you didn't see, I posted in the chat the link to my example if you want to sort of see a potential way you can go about doing it. I will say, if you look at my JavaScript, I did some crazy stuff. Like, you don't necessarily have to go quite as crazy as I did, but that's one way to do it.
I have a slightly unrelated question. I do remember asking in class, and you kind of answered it wrong. Like, when I asked how we can interact with APIs or whatever, yes, it has to do with this, but I meant because for my project, I'm doing EVs, and one of the APIs I need access to is charging stations in the area, and information regarding if one is being used at the current moment, one is free, whatever. And I had to talk, I don't know if you know him, Jason. He also helped me out a bit, but how do I go about talking to those companies so I can ask for access or possible access to user API?
That's a good question. I would say the first place to start is look up EV charging location API or EV charging location data set. Something we didn't talk about in class, but sometimes might be a viable strategy, is if you just need data and someone put together a large collection, sort of effectively a big spreadsheet of data, you could import that and use that sort of like an API. I mean, you're not querying an external service, but you have that data from somebody. And in your case, that might be a more viable strategy if you can't find a service. But I would say, before you sort of have to go down that road, just look it up, see what's out there. I'm not really familiar with anything like that off the top of my head, but I wouldn't be surprised if something like that existed.
I just do some digging. I still have some time before this capstone is due, and I'm at an okay spot.
Okay, cool. Actually, wouldn't be surprised if Tesla had an API, supercharge API. Oh, yeah. Okay. So take a look at this. So I guess I didn't talk about this either, but a lot of data, a lot of sort of web services don't have an explicit API. but sort of they have an API they've built internally for sort of their own company use that sometimes through digging around in an application that like is a public application people can use, looking in like developer tools and looking at all the network requests, you can kind of reverse engineer what their API is. Like if you see something that's like a request to like /resource, and you can be like, I bet I can probably post that, or I bet I can probably put that, or something like that. It looks like this is sort of what it is for Tesla, at least. And I don't know if this would help you fully, but like it looks like that they have some data on like energy sites. And you can sort of get things from that maybe. This would probably be a little bit of a not the best API to use. Like the thing about these internal services is like there's no guarantee of support from Tesla or from anybody else. So it could change like the day before your capstone demonstration, and you're like, okay, I guess I can't use this anymore, and that wouldn't be great. So like it's an option, but maybe not the best option.
Yeah, no, that would suck. It's kind of embarrassing.
I think in practice, so these things don't tend to change. Like the way these sort of services work is usually they make a new version, they sort of have a while for it to deprecate. So you might sort of start to like, I guess if like the web applications that are sort of out there are using these endpoints, it's probably unlikely they're going to change tomorrow. If you know what I mean. I think Schneider might have frozen.
Did you post your example? What, I froze?
Yeah, I think you froze for a second there, or maybe it was me. I'm not sure. My internet's not so great right now.
No, he froze.
Okay. Say what you said again.
I was just looking at your New York Times example, and I see that you have a more info link. Is that part of the? Is that something you did part of the API, or is that just the HTML CSS you did because you wanted to?
So that data, it was one of those things where I was looking at the data I got back and I was just like, how might I visualize this? And I think they gave me like an Amazon link in there somewhere. So I thought like that might be a good thing to expose to somebody. Like you click on that link and it sort of brings you somewhere. But like, as I said, kind of with Exona, like you can kind of take us in whatever direction you want. I sort of like I also said in the class, like if you want to, like if you're sort of really struggling with this and you just are like, the only thing I can figure out how to do is render some JSON on the page, like just sort of dump all the JSON on the page, like that's even good enough. You just need to somehow get the data on the page somehow. Part of what's sort of nice about this assignment is it sort of it allows me as a teacher to like give something to folks who are struggling where they can get something out of it, but also still be challenging to people who are a little bit further ahead. So like it's nice in that regard. So like that's why I'm being so vague, because like I want you to sort of have fun with it if you're like able to get something to work. Oh, I think you might be muted, Schneider.
Oh yes, I was saying understood. This isn't something I can't do. Granted, I still gotta start, so I'll keep you posted.
Okay, cool. I'm curious, Ixona, what you have to say about it, but I think the hardest part's probably figuring out the request you have to make.
Yeah. It's like, okay, so what request do I need to make and how do I want to make it? And for us, it was more of like doing for of loops. So we did a lot of those. But it's also like what exactly, like you said, it's literally like what exactly are you looking for? Like and how can you get that picture or can you get that information to appear on your page? And then I'm like, this is a lot, but it's obviously I learned a lot. So no, it's good.
Cool.
Yeah.
How's it going, Brandon? Have you made any progress in the New York Times project yet? No problem.
Not too much. To be honest, it's like that issue where you're just looking at the instructions and it's just like, okay, what? So I'm just yeah, I'm just trying to take my time a bit, but I'm getting there.
Yeah, I mean,
Starting is always the worst for me. I get in my head about things a lot.
yeah, and it's not a big deal. I guess like I think Max mentioned this before as well, but like often one of the most helpful things you can sort of break down a task into smaller, more achievable tasks. And I'd say maybe this is dropping a little bit of a hint, but there's a little API tester tool on the New York Times developer portal website. If you go in there and you figure out how to get your token, put it into there, you can actually try out the API request and sort of see it work.
Okay.
And that shouldn't be like, well, I mean, famous last words, that shouldn't be too difficult of a prospect. And it's also not a thing you have to write any code for. It's sort of just like playing around with the tool. But once you can get that to make a request, then that sort of gives you some stuff you can start to, some threads you can start to pull, if you know what I mean.
Okay. Yeah, that's essentially what I'm kind of looking for, is like what would be the best place for me to start, or for me to gain some
Yeah.
traction from there.
Yeah.
Yeah.
Cool. Sounds good. Well, I'll
Appreciate
say that I haven't gotten many requests for
Yeah,
one-on-ones. And if that's
Best
something
question?
that oh, I think Schneider, you might have just saying something there.
Yeah, the HTTP and the you'll go over that.
Oh, you cut out a little bit there, but I think you were asking about HTTP and HTTPS. Yes, okay. You sent me a message about that in Slack. Yeah, I didn't talk about this partially just because I forgot, to be honest. But like, so you'll see in all the stuff we were doing, we used the protocol HTTP. And in a lot of the stuff you're going to find out there in the real world, there's this protocol HTTPS. So HTTP, Hypertext Transfer Protocol, the S means secure. So they're both the same kind of protocol. Like behind the scenes, you're doing the exact same stuff. HTTP uses port 80. HTTPS uses port 443. But like what you're actually sending, all the sort of things in the protocol are the same sort of thing. There's a method, there's a path, there's a protocol, there's the headers, the body, like you get status codes, like all that sort of stuff's all the same. The only difference is HTTPS will have some encryption that goes on to sort of ensure that there's that the server and the client are sort of talking on like a secure channel. So I didn't talk about, this is all stuff I didn't talk about, frankly, because I didn't think it was as important as sort of getting the mechanics of making requests down, but it's good to know. Before HTTPS was a thing, if you were a client and you were talking to a server, you were sending raw text over the internet, the raw HTTP content, protocol contents. And that's what we were doing sort of when we were playing with Netcat. And that works, and that's how the internet sort of existed for many years. But when you're starting to send things that are kind of sensitive, like for example, you want to log in with a username and password. So you have like a request you make from a web application. It's like you type in your username and password, you click login, it sends that stuff to the server. You're sending that stuff what's called in the clear. You're sending it in sort of an unsecured way. And what that means is if anyone's sort of just like sitting there watching the traffic, that could be like as simple as like, let's say you're connected to maybe a router at like a place of business or like an employer you don't control or something. Or it could be like someone nefarious at like your internet service provider level, someone like who can sort of see all that data. Like there's nothing preventing them from just looking at your data and being, oh, okay, I see all that exactly what you're doing, and sort of spying on you as you're using the internet. That kind of like, it's not so great, especially when you're sending a lot of this stuff that should kind of be just between you and the server, like secure things like tokens or like login credentials. So what HTTPS does is it uses this technology called TLS. And really what happens is before all the sort of HTTP stuff, there's sort of a thing that happens before that, where sort of the client and the server sort of talk to each other and form a secure socket channel layer. And what that means is you can still do the exact same thing you're doing with HTTP normally, or sending all that stuff, but you're just, instead of sending it directly from the client to the server, you're sending it through sort of a transport that's secured. I could go a lot more into this, but also I don't know if you all have gotten experience with some of the security information, like behind the scenes security stuff you need to know for it to make sense. I believe, I don't know for sure, but at least in the past, there's been like a security module in Careers in Code. And assuming you're going to have that, I think you're probably going to talk about TLS and SSL and all that in that module. Let me quickly look at this sheet and see if they're doing that. Oh, say that again?
I think we're going into React next, learning the React framework.
Yeah, you're going into React next, but usually, at least in the past, there's been like a week-long security module, and it's been taught by like Nathan in the past, or like there's someone else who taught it last cohort. I gotta see, because I might be misremembering, or maybe Max decided that we're going to cut that this year or something. But if you do that, they're definitely going to have a thing on SSL, because that's like probably the most important part there. Let me see if I can find it here. Teacher mapping. Okay. DevOps, JavaScript, APIs, React, database, full stack. Okay. Potentially. It's unclear. There's no explicit week labeled security, but I think that Nathan might talk about that as part of the DevOps week later on.
We already had our DevOps weeks.
No, there's another set of DevOps.
Is it part 2?
Yeah.
Oh, okay.
It
Yeah,
got
that might
split up this time. Yeah, and if he doesn't, and you're curious about it, maybe after Careers in Code is done, let me know and we can chat about it sometime. Because it's or I mean, if we don't have anything to talk about now, I can get into it. But like, I don't want to do that if other people have things they want to talk about. I mean, I'll talk about it. Like, okay, sounds like that's what you want to hear about. If anyone else joins, I'll pause and let them sort of chime in if they have questions. But like, I guess, so like a lot of this sort of stuff is like, comes back to cryptography. And like, this is sort of like a kind of branch of mathematics that sort of has its roots in like early like code breaking and wars and stuff like that. So you have like two generals who are like sending messages back and forth to each other or something, and somehow like they have to like take this message and send it in a way where like the other person, like the other side, can intercept it. So that's like really early. You had sort of people like Julius Caesar, like in Rome, who would send messages from like him to generals or whatever, and use this thing called a Caesar shift cipher, which is like a really sort of basic example of a way that like encryption could be done. I should also define encryption too. Like, encryption is this sort of idea where you're taking data, you're sort of like scrambling it up, and then you're sort of on the other end, someone can like unscramble it and make that data again. And the better the encryption, the more that scrambled up data just looks like random noise. Like, it's sort of unintelligible, something that you can't decode back. But anyway, like an example of like a cipher or like an encryption mechanism is like a Caesar shift cipher. So what that is you have an alphabet. Let's just say it's all the lowercase letters. So when you want to, and maybe like a space. So you want to sort of assemble your message. You've got 27 possibilities of 26 letters in a space. And you sort of write out your message. And then you take all of your letters and you sort of arrange them. So from A to Z and then the space at the very end, let's say. And what you do is for every letter in there, you move that letter sort of further on in the alphabet. So like, let's say you're going to shift by 3 and our message is like apple. I'm making stuff up here. I don't have any slides. I didn't do any preparation. So you're going to have to bear with me here. But like, okay, so like the first letter in apple is A, and we're shifting 3. So A to B, B to C, C to D. So like A becomes D. And then P to Q, Q to R, R to S. P becomes S. and you have another P, so P becomes S. So you end up with like D, S, S, and sort of so on and so forth. I think you can probably understand where I'm going with that. And you have this sort of thing where like this looks kind of like random text, and it's not something that like people can really understand. And if I just give you this thing, you're like, okay, I don't know what to do with this, but someone who understands how the cipher works and knows that number of characters you shifted can very easily shift backwards and figure out the original, like the original thing. So there's a couple things, like I picked the cipher in particular because it's an easy one to understand. And there's also some things that are very bad about it. Well, I mean, let me start with the good things. The good things is it's simple. Like anyone can understand it. You could write probably a function in JavaScript to compute a Caesar shift of a word. I mean, it might take you a little bit, but it's a relatively simple thing to compute in the greater scheme of things. The bad things, though, are, first of all, I picked Apple kind of on purpose because it's got 2 P's in it. And you'll notice that that sort of pattern transferred itself to the ciphertext. Like we had sort of the first 3 letters, you had the first letter, and the 2 P's transmuted into the same letter. So what that means is, if you see 2 of the same letters in the resulting text, you know that those make up, like, those are the same letters in the source text too. And that's not so random. Like, that's sort of a place where that's like, you're like, oh, that's sort of, there's information that's leaked through there. And that's not so great. The other thing that's worth mentioning is sort of the number you use to sort of like transmit or transform the data. Like that number, if you only have like a 27 character alphabet, let's say, like there are effectively 27 possibilities, because sort of, I guess I didn't say this, but if you get to the end, usually you wrap around. So like if you're at Z and you want to go to 3, it'd be like Z to space, space to A to B. So because you wrap around like that, any like number of any number in the Caesar shift that's like greater than sort of the number of characters you have, like let's say 28 is effectively 1, which means you actually only have like 27 possibilities for how you can encrypt, like, which is a really small search space. And there are people out there who like are into this stuff who will build programs which will sort of take like these sort of more toy ciphers and build programs to reverse them by just literally brute forcing, like going through every possibility, like shifting everything by 1, looking at it and being like, does this look like the right thing? No, okay, let's shift it by 2. Okay, does this look like a good thing? No, okay, shift it by 3. Does this look like a good thing? Oh yeah, this does. Okay, this is probably the message. Like,
Yeah, I'm looking at it right now. It looks like it could be like a little puzzle game, honestly.
so it could be what?
A puzzle game, like the way it looks like. I'm looking at like
Yeah.
images stuff, but
Yeah, I mean, it's not that complex of a cipher, but I'm bringing this up because it's got some interesting properties to it. One other interesting property to it, which isn't necessarily bad, but it's just like a thing to note, which is that if you know that number, you can both encrypt and decrypt. So what do I mean by that? Well, let's say I have my word apple and I encrypt it. And then I sort of send that off on my my messenger on the horse, sort of like galloping along to go to the other general to send them the message. And someone intercepts that messenger and like, okay, this is olden times, and like kills that messenger and is like, I'm going to send a different messenger with a different message, and is able to sort of decode that message sort of through some brute force. They know that number. So they can like re-encrypt another message and send it along, and the general will receive a message without fully realizing like, oh, wait a second, it was intercepted. Like someone can re-encode a message with that same number. And that is sometimes an okay property in certain systems and sometimes not a good property. In this case, it's not a great property. So that kind of like, so now that I've talked a little bit about some basic encryption stuff to get you sort of your mind in that sort of sphere, let's talk about sort of what some of these things are actually called, give you some terms to put to these properties. So the whole like the idea where like you can encrypt it and you can't decrypt it with the same number, that has a name. It's what's called a symmetric or asymmetric cipher. So an asymmetric cipher is a sort of encryption mechanism where you need a different information to encrypt and decrypt than you do to decrypt. And a symmetric cipher it's the same. It's symmetric. Kind of makes sense. There's also what are called block and stream ciphers, which is a good thing to know about. So a block cipher is a cipher that sort of you have to give it like text of a certain size. Usually it's like a power of 2. So something like you give it 1024 bytes, and it will sort of encrypt that and give you back 1024 bytes of encrypted data. And then sort of you can go the other way. And if you have less than 1024 bytes, usually you end up like padding those extra bytes with zeros or something like that, just sort of like filling it out. You need to give it exactly 1024 to fit for the block cipher to do its work. The other type of cipher that's most popular is called a stream cipher. And a stream cipher is more like you can just give it like characters. So imagine you sort of give it like one character at a time. And as you give it more characters, it's sort of like slowly, its encryption like text sort of increases in length. And there's another thing where in certain properties are like certain ones are better in certain situations. So the most popular symmetric block cipher is called AES. Stands for the Advanced Encryption Standard. You'll notice that a lot of these encryption algorithms have like super like opaque names and like make it sound like they're the best thing in the world. It's kind of funny. What's cool about AES and why I'm bringing it up is because it's a relatively straightforward cipher that is actually secure, that you could use for actual things these days that would not be that hard for you to get into. What's cool about it is it sort of has like it's like a function that sort of takes two things. It takes the thing to encrypt, and it takes what's called a key. And that key has a certain length to it, usually measured in bits. So let's say you might have like a 512-bit long key. So that's 512 ones and zeros, all arranged in order that sort of make up a number. And that number is sort of the thing that allows you to encrypt and decrypt. So with AES, you give it the thing you want to encrypt and that number, and you put it into the function, and it gives you out a thing that's like what's called your ciphertext, your thing that looks random. And then you then can take that ciphertext, put that back into the AES, same key, and it'll give you back your original text. So in other words, it's symmetric. Sort of you can like call the function with the ciphertext, and it will decrypt it. It's sort of like will go both ways. The way that a lot of these ciphers generally work is they gain their security less from like how they work behind the scenes, like the Caesar shift, where like that's a thing where part of the secret of it is that like of how it works, like you sort of have to you're supposed to not know about the shifting of the characters, but if you know that it's doing that, then actually brute forcing through all the possibilities is difficult. That's a bad design for a cipher. The way ciphers should be designed, at least in the way people sort of approach it these days, is how the cipher works should be broadly known. And the place the cipher should get its security is more from the length of the key. So AES, you could, if you wanted to, look up the algorithm for AES and read like an academic paper on how it works and implement it yourself. Or more realistically, if you're curious, there's some really good computer file videos on this. But you could implement it and it would work. It'd probably be a bad idea to do that for anything real because you might make a mistake and then you're sort of leaving people open to stuff being not secured properly. But you could. And like AES with a really short key is going to have a very short like brute forcing range. Like there's sort of not much. You could very easily brute force like something with like a 64-bit key. I mean, I'm making these numbers up. I'm not really a security expert. I know enough to be dangerous, but not enough to actually know what I'm talking about. But like you could sort of use like a short key and not be all that secure. So something like, again, this is one of those things where it'll probably be out of date in a few years, but if I remember right, like a 512-bit key is about the shortest that would be at all secure, like some way insecure, or some way secure in some way. And like 2048 bits is more like, or 4096 bits is probably more where you want to be these days. But it's one of those things where as computers become more powerful, it's sort of faster for them to brute force through things. So sort of the length of your key always has to increase as time goes on. So probably in like a couple years, we're going to be using 8,192-bit keys or 16,000, whatever 192 times 2 is. So like it's one of those things where that's a thing that's sort of a constantly evolving target. So that's an example of a symmetric cipher. I guess before I keep on talking, does any of that make sense?
Yeah, I'm following you.
Cool, cool. Schneider, I think you're muted, and your internet's not having a good time. So I think I'm gonna assume it's a thumbs up. Yeah, the length of the bits. Oh, okay. So the length of the bits is a direct correlation to how secure it is. Yeah, yeah. So a 512-bit long cipher is going to be less secure than like a 2048-bit long cipher. I'm not 100% sure on this, but I believe it's not linear. Like it's one of those things where a 2048-bit cipher is like significantly more secure, not twice as secure. But don't quote me on that. It probably depends on the algorithm there. So that's like AES is probably the most well-known and well-used block cipher that's symmetric. Let's talk about an asymmetric sort of algorithm, because those actually get used a lot more these days. So as a reminder, like asymmetric means you have a different value that can be used to encrypt versus decrypt. So an example of the most popular symmetric algorithm is called RSA. And I got to look up what that stands for because I forget. Yeah, the Rivest-Shamir-Adelman algorithm. I have no idea who those people are. So it's actually pretty old. It's like from the 70s, I think. But it's one of those things where it's aged pretty well because you can increase the key length and it still works pretty well. So asymmetric encryption, the way that tends to work is you generate two things sort of before you do any of the encryption, what's called a public key and a private key. So the public key and the private key effectively are just really long numbers. And when I say really long, oh, okay, Schneider's gone. I can keep going. I mean, I guess it's recorded so we can watch it later. And Brandon, it sounds like you're at least kind of interested.
But yeah, I'm listening.
Okay. So the R will generate this public and this private key, and sort of they're two separate really long numbers. And when I say really long, I mean really long. Like, let's just give you a guess of like, let's say you put like one with like 200 zeros after it, long, like very, very large numbers. And the larger the numbers, or the larger number of bits effectively that are used to represent that number, the more secure the key is. And what you do is you take your public key and you take your private key. Got to make sure I get this right. And the RSA algorithm implements two functions, an encrypt function and a decrypt function. You take your private key and you pass it into the encrypt function along with the thing you'd like to encrypt. And that gives you a resulting ciphertext. Then when you want to decrypt, you take that ciphertext and you put that into the decrypt function with the public key. And then that gives you the sort of the original one, back to the original text. So the idea is like, what the private key lets you encrypt and the public key lets you decrypt. The reason why they call it the public and the private key is because the public key is a thing that is supposed to be public. Like the idea is that if you are, let's say, publishing messages, then you really kind of want to allow anyone to read them usually. And if you can write the messages, like you only want to be the only one who can write the messages. So for that reason, you want the private key to stay private. So think of a private key like a token. It's like not a thing you want to share. It's a thing for you. And anyone who has that can kind of impersonate you. And then the public key you then use to decrypt the things that are sent by people. So that's generally how asymmetric encryption works. I can keep on going a bit more and talk about maybe how that relates to SSL and all that, but I just noticed Alba joined, and I want to give her a chance to ask any questions about what we're supposed to be talking about today.
I do have a question about homework 11, if you don't mind.
Sure.
I completed them. Sorry, I didn't want to interrupt your.
My soliloquy, no problem.
But I took screenshots. You said that you wanted 3, however, you only asked for how to use it, like how to get the output on 2 different from 2 different types. So
I
on
think-
Postman and on curl. So what's the third?
Oh, maybe I meant only 2.
Okay.
Maybe I mistyped something somewhere. I'll say if you want to do it with fetch too, it's probably not a bad idea. Now that you have that knowledge, but I think at that point we had only talked really about curl and postman. I didn't want to sort of.
We did
Put
talk a little
fetch.
bit about fetch at that time. Just like literally the last 45 hour.
Yeah,
after
yeah,
break. But yeah, I mean I can do that too.
yeah. I mean,
I'll do that.
I think only curl and postman are required, but feel free to do whatever
Go
you
above
want.
and beyond.
You're welcome to if you'd like.
Okay, perfect. Gives me practice, so yeah, definitely.
Yeah.
Thank you.
Yep. Alba, how's it going? Oh, I don't know. Maybe she can't hear me.
Sorry, I was trying to get ready. I was joining from my niece's baby shower.
Oh,
I'm in
congratulations.
Massachusetts. I was doing the decorations for like Star Wars themed baby shower.
Nice.
But
Cool.
I was when there I couldn't hear you guys. It was too loud.
No problem.
I did try to start doing the linking the different links for the project itself. It's been working pretty well. The only thing I noticed is once I downloaded the API information and I had all the information, I'm having a hard time getting the links to actually work for when you press more info. It's not working. So what I've been doing is I've been getting the titles. I've been going to Amazon and then I've been getting their image addresses. And that's been working better for me.
Huh. So without seeing some actual examples of code, it'd be hard for me to comment. But if I could just give you a suggestion.
Yep.
This is so you're talking about the image URLs or the more info links?
So the image URL, I could click on the more info link, but it takes me to Amazon and it says, oops, this page is no longer available.
Okay.
So it does take you to the link. It's just not taking you to the proper link.
Okay. It might be
So
possible.
what I've been doing is I've been putting the book information on the Amazon page itself so I could get what book it is and what the image is.
Yeah.
And
Okay.
then I've been copying the image address from there, and that's been working better for me.
Yeah. That makes sense. I guess like I would guess the reason why it's not working for you is you might be using like the wrong field in the API response. There's a lot of them in there. And I can look up in my code and figure out what I used if you sort of want that for reference. But
Okay.
I know that there was in the response, there is one of the keys that maps to a value that is an image that works. I just don't remember
So
which
I
one it
was
is.
looking through the thing and I was going through the ranks, like rank 1, rank 2, rank 3, rank 4, rank 5 on each category. And then I was going to the image URL. It said like a book image or image, and then I was copying that URL and putting it in. It was forwarding me through Amazon. It was just going to an oops page.
Yeah, I guess like I think it's going to be hard for me to give you helpful feedback unless I can see some code. I guess that's where I'll leave it.
Okay, so what I'll do is I'll actually try to set up a one-on-one
Cool.
to figure
good.
that out. But I've been figuring out the links through Amazon. I've been able to get the different books and the ranks. I've done at least 5 of the different categories of the 5 books. It's 18 of them, so it's gonna be a while
Yeah,
to
I
get
guess
all of the links.
if you can get the API working, you won't have to go through and manually do them. So it
Yeah.
might be the sort of thing where it'd be worth spending like half an hour figuring that out, and then that'll make it work better, you know?
Yeah.
Cool.
Yeah, so that's the only issue that I've been having, but I pretty much created all the lists I created all the books. I created all the list tabs. I created all the books tabs. I created all of the Arefs, the image tags, and everything. All I have to do is pretty much plug in the information.
Okay. Cool. Sounds good then. I mean, you showed me where you were before, and it seems like you're well on your way there. Which is good. I'm going to post in Slack a screenshot of the API response, and I'm going to highlight the two areas, one with where I got the image from, and one where I got the Amazon link from.
Okay. Yeah, that should be a little bit easier. That way, when I could start tomorrow again, after I'm done with all this mess right here, I could start actually going back in and plugging in a little bit more of the books and stuff. If I have the right URL to post in, then that's one less step I have to do into putting it into Amazon and getting all the different URLs.
Yep, sounds good.
All right, thank you.
Yep,
Bye.
bye. Okay, well, I can keep going, Schneider, if you want. I mean, we still have like 15 more minutes here. And unless anyone else still has any, unless anybody else has any questions.
Yeah, if nobody has questions, knock yourself out. I'm listening, and I'm doing my research on the other
Okay.
side.
Yeah. So I guess it's talking about asymmetric encryption. I guess I should also say, like, did the asymmetric encryption thing make sense?
No, because I got kicked, and then I joined
yeah.
back in while you were discussing it. So
Fair enough. I guess the important part is, like, there are two things, a public key and a private key. They're both really long numbers. The public key is used to decrypt. The private key is used to encrypt. So it's asymmetric. There's different to encrypt and decrypt. There's sort of like two functions, one for encryption, one for decryption. One takes your plain ciphertext and the private key and gives you the encrypted thing. And then one takes the encrypted thing and your public key and gives you the decrypted thing. Yeah, and that's kind of really the most important thing to know about asymmetric encryption, but also that, like, it's really important in a lot of things, like TLS. So, like, what it's doing behind the scenes is setting up some asymmetric encryption, or sort of, or how does it do it? I guess it's like, I guess I don't even really know how it works, which is not great, which is probably why I didn't teach it. But I think what it's doing is sort of something where it's like doing a key exchange, which I guess I can talk about after this, then using symmetric encryption to sort of somehow share data, and then I think go from that to asymmetric encryption. So it's like a bunch of different things, but I think at the very end it uses asymmetric encryption to sort of communicate from client to server. And what that means is sort of like every request is taken, is encrypted, then sent, and then the other end will then decrypt it and then sort of parse it. And then before it sends the response back, it'll encrypt it, send it over, and then decrypt it.
okay, so I just Googled TLS. So it's a protocol. So just like what you taught us, it uses the method and then uses the same pretty much format, I guess.
Well, so I think it'd be better to think about TLS as not like a thing that is like a related HTTP, and more as like a protocol you can use to send arbitrary data from a client to a server, or sort of across a TCP socket securely. So you can like open up a TCP socket, then within that set up TLS, and then with sort of within that TLS layer, send whatever you want. And you could send HTTP, you could send anything else you want. You could send like that crazy protocol I was talking about on day one, where you like ask the questions. Like you could do that over TLS if you wanted to. It's just sort of like another layer you can set up within the tunnel. Sort of you're like that. You instead of sending things directly to the socket, you sort of send them to the TLS layer, which sort of does the encryption and then sends that through the tunnel. Make sense? Cool.
Got you. Yep.
Yeah. And this is also pretty bad, but I'm not exactly sure off the top of my head what the difference between TLS and SSL are. They're related. One means something, one means another thing. in effect, they're very similar. I think it might be one of those things where it's like the difference between like HIV and AIDS. It's kind of like the difference between TLS and SSL, maybe, where like one's kind of like the mechanism and one's like the thing, kind of. I don't know. Don't quote me on that.
I don't know. It's saying TLS is an improved version of SSL, so I'm guessing
Oh, maybe I'm just totally wrong. That could be too.
SSL, right? Not SSR.
SSL, yeah, secure sockets layer.
Yeah, saying TLS is an improved version of SSL. Says that it works the same as a SSL using encryption to protect the transfer of data and info. The two terms are often used interchangeably in the industry, although SSL is still widely used. So
Yeah.
I guess just stick with TLS.
Yeah. That does bring up something though, and this is like I'm very quickly sort of getting on a thing here where
Yeah, I was just gonna say one thing that's rather important. Apparently, SSL is deprecated. So yeah,
huh.
and this is of March 17, 2022. So it's not out there.
Huh. Okay. Yeah, I just sort of like use whatever's given to me and have not really done a ton of research on this, but maybe I should. So there are two other quick things I want to mention if we're going to talk about encryption, because they're both sort of kind of important. The first thing is what's called hashing. So imagine you could write this function that could take some sort of data and then scramble it in a way that sort of gives you some scrambled data on the other end. But you do it in such a way where, given the same input, the function will always produce the same output. So what that means is, like, if I hash like the word apple or the word banana, like if I hash apple, I'm always going to get something. If I hash banana, I'm always going to get something else. And if I hash apple again, I'm going to get that same thing I did the first time. This is a really sort of helpful thing in a lot of different places. I'll say the most, like, a great example of where this is helpful, and this sort of falls under cryptography because it's sort of dealing with like scrambling data. But let's say you have a file and you want to send it to somebody. Like the internet, we didn't talk about it, but the internet's sort of a lossy thing. Like if you sort of send data over the internet, sometimes data gets lost or gets corrupted. And it's possible that the data you get on the other end isn't exactly what you're going to get coming in. In practice, with the small request we're sending, it's always going to work, but sometimes that isn't a reliable thing. So one thing you can do is, if you're sending large bits of data over the internet, you can actually take that data locally before you send it and hash it and commute what's called a checksum. Effectively, think of it as like all the sort of data in the file just sort of like combined together, but like shortened to be like a small little length of text. And then what you can do is you can sort of send that checksum first, and then you can send all the data after it. And then the other side can then do the same thing, go through, calculate that hash for that data, and then compute another checksum. And if those checksums don't match, then it knows that it screwed up somewhere and some data was lost. And if they match, then you know the copy happened correctly. So that's often a strategy that's used a lot, and sort of that, like, more abstract versions of that same concept are used in a lot of places. That exact thing I explained maybe isn't done a ton, but like things like that, we're sort of using checksums to make sure data didn't change. That's used all over the place. And the reason why that's important is because checksums are a fixed length. So like probably the most well-known checksum out there these days is called SHA or SHA-256. So what it is it gives you back a 256-bit number as a response. So like you query that function, you give it your thing, and it will always give you back 256 bits that will always be the same no matter the input you give it. Now, what's important is that there might be two things which will generate the same hash. That's pretty rare and probably is not going to happen. It's what's called a hash collision. It happens sometimes, but generally they are going to be relatively unique. But the idea is, like, with the same input, you're always going to have the same output. So that's the thing, one I want to talk about, just hashing in general. That's a word you're going to hear. And the other thing is maybe a little bit more nerdy, but I think kind of interesting. So let's say you have a open TCP socket, and you want to establish SSL on that socket. Now, everything we've talked about so far requires you have two like a client and a server that both sort of know something secret. And it sort of relies on the fact that like a third-party observer doesn't know the thing that's secret. Now, you might be seeing where I'm going with this, but like, how do those two parties decide on a secret without that third-party observer knowing about it? Like, if you think about it, like maybe the most naive version is like you think, okay, the client can generate like a secret value and send it to the server, and then sort of the client and server can use that value to secretly communicate. But the third-party observer could just see that value and sort of steal it, and now it can use it to see everything that's going on. So you need some sort of way you can transmit data between the two parties without the third-party observer knowing that data. And it turns out there's a really clever way to do this. This general problem is called a key exchange. This is a thing that has to happen in a lot of systems. And I'm bringing it up because not because I expect you to memorize this or anything. I mean, none of this stuff is important. Like, you're going to learn it later on in careers in code, probably, if it becomes important. But like, I want to give you insight into sort of the complexity of like these algorithms and how if you screw up even the smallest thing, how it can make it completely insecure. So the algorithm I'm going to tell you about is called Diffie-Hellman. You can look it up if you want. The Diffie-Hellman key exchange. It's probably the most well-known key exchange out there. It's been around since like a lot of this cryptography stuff, like since the 70s or 80s. It was invented by two sort of like collegiate scholars, I think, Diffie and Hellman. And it solves this problem. And what you can do is sort of using this mechanism, using a clear, like in the clear transport socket, you can generate a secret number that both the client and the server both share without ever sending that number in the clear across the socket. Okay, let me explain how it works because it sounds kind of magical. But like a lot of cryptography stuff, it relies on math. And this is like this is why this stuff can get kind of involved. This math, though, is like simple enough where I can wrap my head around it. So there's a mathematical property. If you take a number and you raise that number to a power, so like with an exponent, and you raise that whole total to another exponent, so like let's say a to the n to the p, that's going to be the same thing as a to the p to the n. You can switch those exponents around and it'll result in the same result. And that's what Diffie-Hellman uses. So let me sort of walk you through this here. I'm going to sort of say it, and then probably this is going to be hard to follow without actually seeing it drawn out. So I might have to draw it out or something. But like, you have the client generates a sort of initial random a value. And then the client also generates an n value, sort of like a number to raise to the power of that number. And that both those numbers have to be really long for this to be secure, like really, really long, like a number with like a 4096-bit number sort of thing. Like if you just did like A is 1 and B is like 5, that's not going to be secure at all. Okay. And I have to make sure I'm saying this right because it's been a while since I've thought through this. But I think what happens is the client takes that A and raises it to the n, and then sends that number to the server. The server then generates a p-value. The server then takes that a to the n and raises it to the p and sends it back to the client. Or wait, no, I got that wrong. Okay, erase what I just said there. The client generates the a value and the n value. The client sends the a value to the server. The server raises the a value to the p and sends that back to the client. And then the client, gosh. Okay, I'm just going to look this up because I don't want to keep saying this wrong.
It's been a minute, huh?
Diffie-Hellman key exchange. Let's see what the internet has to say. The internet's always right. Okay, Wikipedia's got to have a good article on this. General overview. Yeah, here we go. Okay. So typically with cryptography, whenever you see this stuff written out, the problem is always you have one party named Alice and one party named Bob. This is always how it's done. It's just like a weird thing, like how the crypto people do it. And Alice and Bob always want to send a message to each other. So, and wow, there's even a Wikipedia page on Alice and Bob. That's amazing. Okay, anyway, so Alice and Bob do publicly agree ahead of time to use sort of some like the base. It's the same. Oh, there's a mod part to this too. Okay, I forget what this is about, but I don't think that matters for the rough idea. But like, Bob will pick a secret integer, or Alice will pick a secret integer, and then send Bob sort of the base to that secret integer. And then Bob will send Alice. Yeah, like, okay. So they both compute like a to the n, and then the other one computes a to the p, and they sort of swap those numbers with each other over the channel, and then they compute then they take each of those powers and they raise them to the one they have. Yeah, okay. So explaining that without me mumbling and stuff, like the client. So the client, like the Alice and Bob are sort of the client and the server. They both have sort of an initial like a value, or like the base value for the exponent. Then they both generate a value to raise that exponent to. They both raise it to that exponent and they switch their values. And then they both sort of then once with the switch values, then raise those switch values to the other exponent. So that like one of them ends up computing a to the n, and then sends that to the other one, and the other one ends up computing that value then to the p, and then the client then takes a to the p and sends it to the other one, and the other one then computes that quantity to the n. So you end up getting is one of them has a to the n to the p, and the other one has a to the p to the n. But because neither p or n were ever sent in the clear, for an attacker to figure out how to sort of reverse that, they would have to take the square root, or I guess not the square root, but like the nth root of that thing, that power. And it turns out this is like a thing that underpins a lot of cryptography, that taking a number and raising it to a large power is a lot faster for a computer to do than doing the reverse of that. This is what's called a trapdoor function, which is like a key thing in cryptography. And it's how like a lot of this is even possible. It's like a math function where to do it one way is easy and the other way is really hard. And when I say easy, I mean like you could compute it in like a couple milliseconds. And when I say hard, I mean like longer than the lifetime of the universe to reverse it, sort of thing. Where it's like very asymmetrical. So that's like how a lot of this stuff works. And like you can sort of read into this more if you want, but what this effectively like it's sort of using that property of math to sort of provide like some sort of interesting functionality between these two parties that are communicating. So I'll post this also in Slack. Again, none of this stuff is like important. Like it's not something I'm supposed to be talking about. If it becomes important later, there will be an official lesson on it. But yeah, if you're curious.
So I have a question. Is there a set rule to the exponential value? Like, are you always gonna multiply by like 2 and then goes up from there, or how does that work?
I'm not sure off the top of my head. I'm not really an expert at this stuff. What I'll say is intuitively, I would guess you probably that number is probably a fixed length number. So it's probably like always like a 4096-bit number. So it's the number that like you define, like both parties decide ahead of time, like we're going to use Diffie-Hellman with numbers that are like so long. And I would guess the longer you make those numbers, the more secure the algorithm is. But also the longer it takes to compute. So it's like the trade-off. And as computers get faster, that time to compute decreases, which means that the shorter numbers become faster to crack. But it also means that like the longer numbers become less time to use. So it's like there's a weird trade-off there. I'll also say it's worth maybe mentioning that RSA, there's an algorithm that was released like 10 years ago, maybe, that if you have access to a quantum computer, in theory should be able to break open RSA and make it no longer secure. It's never in practice been run, like because we don't have quantum computers right now that are fast enough to, or like capable enough to actually run it. You need like something like 24 qubits to run it. We only have quantum computers with like maybe at max like 4 or 8 right now. But it's one of those things where it's like a looming thing. And for that reason, there's a lot of people who are sort of like declaring RSA as end of life like starting now, and sort of are trying to get people to move over to other things that are more quantum secure encryption mechanisms. This is like really in the noise. This is not that important of a detail. And in practice, the encryption algorithm you pick is going to make very little of a difference, but it's maybe worth knowing. And like, there gets to be some weird stuff in here with like kind of the cryptography, like political world, where you have people like the NSA who sort of are like experts in cryptography and will do things like release their own ciphers, and people will be like, read through them and be like, I can't find a problem in the cipher, but I don't trust it because I think NSA is sort of like inserted a really obscure vulnerability here they can use to exploit it and sort of collect people's data, sort of like a backdoor into the encryption algorithm. And like, that's scary to a lot of people, me included. So that might be a reason you may not pick that algorithm. Even like, no one can prove it, but like, it could be. And so it's like, it's a very weird world. It's not really software development. It's like cryptography and like security research and all that. And I think there's enough of an intersection where it's like worth knowing a little bit about this stuff. Like sort of what I talked about at the beginning, like, oh, here's what asymmetric and symmetric encryption algorithms are. Like, here's some of the most popular algorithms, like what hashing is. Like all this stuff is kind of good to know as an engineer. It's not all that important to know all this like other stuff. I know it because I'm curious about this stuff. And if you look it up online, I had an old coworker too who was like, kind of went down the rabbit hole on this stuff and was like getting stressed about what encryption algorithm he was picking because he didn't want it to be like, I don't know. Yeah, you don't have to care that much about it, I don't think. I will say, if anyone's curious, the sort of thing that's being moved to from RSA is what's called elliptic curve cryptography, which is like a whole different thing. It like doesn't rely on that whole like exponential square root like difference in performance thing. It relies on a different trapdoor function, which is quantum safe. But yeah, I've already gone way too in the weeds. I don't need to keep going, I don't think. Any questions?
You have RSA put up right now, and they're comparing it to the Diffie thing, and they're talking about where they really differ, that RSA needs a public key beforehand. I don't know what that means, but
Yeah, so Diffie-Hellman is a key, like each of these algorithms I mentioned sort of do different things. Diffie-Hellman is a key exchange protocol. So it's what you use if you have a client and a server and you sort of want to agree on a shared secret you can use for communication. RSA is an asymmetric encryption or asymmetric cryptography protocol. So it means that you use a public and a private key, and sort of the person with the private key can encrypt data and the person with the public key can decrypt data. And then something like AES is a symmetric cipher. So it means that this sort of there's like one shared value that can be used to encrypt and decrypt. So what you can do, like one thing that commonly gets done is you can use a key exchange mechanism like Diffie-Hellman to get a shared secret that you can then use a client and a server to use AES to communicate securely. Because like once you've agreed on a shared secret, now that's your secret encryption key and both parties know it, but no third-party observer knows it. Does that make sense?
yeah, I got you. I'm just going on a tangent right now. We're just searching a bunch of stupid stuff up. I mean, I don't think I'm ever gonna go into encryption, honestly, but like,
Yeah.
I still think it's interesting that I'm just seeing that a quantum computer can break RSA in 8 hours, RSA 2048, whatever that means.
In
And
theory.
then, but like, yeah, in theory, and they're saying that to break it without the quantum takes longer than the age of the universe. I'm like, okay, that's so crazy, whatever that means.
Well, the reason why that is because effectively the way you have to do it, like it's built in such a way where the only way to reverse it is to brute force through every possible combination. And what it means is like every time you add a bit, you remember how before we were doing that thing where we were sort of doing the counting with binary, and when I added a bit, it sort of went from like 1 to 2 to 4 to 8 to 16, like there was sort of an exponential thing there.
Yeah.
So the more bits you add, like if you add 1 bit, that's going to double your search surface area. So it's like every additional bit sort of like has a large, massive effect on the amount of time it takes to like, that's why sort of like doubling the length of a cipher key like has such a massive deal, such a massive effect.
Right. And that's all because of the whole exponential
Yeah, because of that
exponential
2 to
value
the
thing,
n
right?
power that you get with the binary numbers.
Okay. I got that part now at least.
Yeah. So I'll say, like, I guess where I'll leave it is if any of you are curious about this and want to go deeper, there's two YouTube channels that's just taking a look at. One called Computer File, which I mentioned before. And I'll just say, like, it's in general just a really good channel, but it's like a bunch of videos done by all these folks at the University of Nottingham in the UK, where it's like a bunch of professors, and they will just like spend like 15 to 20 minutes just talking about some topic that they're passionate about. And they'll like it'll be like them lecturing and them sort of like writing on a notepad with like a camera over their shoulder. And they're just like always so well done. And the other one is a related channel called Number File, which is a little bit more math focused. Sometimes some of the stuff goes a bit more in that direction, but I'll say that like generally Computer File, I get a lot of interesting stuff from there. I've learned of a lot of like unusual, interesting algorithms from that channel, like watching that and sort of use them in my work, and it's actually been really beneficial. So I'll post links to both of those in Slack as well.
So for us, taking this back to careers and code,
Yeah.
You said that your coworker would stress out about which encryption to use. Okay, so how does that relate to us? Are we gonna have to worry about which encryption to use down the road?
Down the road, maybe you will, but I'll say that like out of all the problems that you have to worry about, that one ranks pretty low. It's the sort of thing where you can get away with a long time with just using whatever is sort of recommended to you by whoever is sort of on a project that maybe has more background, or like if you're using a framework, whatever they just pick by default. Like, I'm going into all this stuff because you asked and you were curious. Like, taking it back to careers and code, very little of this stuff is going to be important to you in the next 6 months. Probably within the next few years, I would say as well. Like, these are more the things where at some point, if you're trying to do something like build an auth system, like sort of build your own like token implementation and sort of do things that are maybe non-standard, you've got to be able to think through the stuff, like think about like what an attacker would do, and try to build a system in such a way where like you can't even get into it yourself. And that's where understanding some of these things are really important. But yeah, you probably don't need to know about much of it now. Oh, I think Schneider froze. Okay.
Sorry, this is like all way too complicated for me. So
That's
I
fine.
I'm trying to anyway, so I did that. I do need your help because every time I try to do something, some like styling, it just did not work. Like it would not show up on my page. And I don't know why it's not. I don't know
Yeah.
if maybe I'm doing the wrong thing. So I was hoping that I can possibly get some help from you, if you don't
Sure.
mind.
Yeah. If you share your screen, we can take a look.
Sure. Give me 1 second, sorry. Oh, come on. Okay. Come on. And okay. Oh, okay. Can you see that? I gotta make this smaller. So what I try to do is I wanted to put I wanted all of this to kind of be in a container. So I put in a div, I did a container here. I just removed it. But I wanted to do a container with a different background color and kind of have some margin on it, but it just wouldn't work. So hold on. And then
This might be a stupid question, but you did include your CSS in your HTML somewhere, right?
nope.
I don't see a link tag.
Yep. That's probably why. Okay, so it's a SRC CSS? No.
Yeah, it's a link rel style sheet src equals, I think,
HL?
src. Oh no, href. You're right. You're right.
Yep. And then SRC.
Let me look this up. I have not written a link tag in way too long. I think it might just be href, not src.
Sorry about that.
Yeah, just href. So you want like href style sheet dot style css.
That style?
Uh,
Wait, what?
Yeah.
I'll figure it out. I'll find it in the previous homework assignment. File, the window.
Oh, it's relative rel style sheet and then a href.
Why can I not type today? Oh my gosh.
So it's rel.
Sheet and then href is the style.css.
Gotcha.
Man, you know we
Yeah,
haven't
snippet that I think is what you want.
We haven't done HTML in so long.
Yeah, seriously, you know it's bad when we can't even figure that out.
I mean, I have previous homework assignments that I can go back to, but this is probably something that I should memorize by now.
I mean, if it's any consolation, I'm having trouble with it too. I haven't written a link tag in like many months.
Yeah, so let's see if that works. Okay. href. Oh,
You may want to
style.
go to the space in front of your styles.css. Yeah. I think that'll work.
Okay. So that does work. Maybe I should do body. I should make that the body. Oh, perfect. And then the container is going to be white.
I don't know where the hell we got source from, but anyways.
Okay. Maybe not that color. Okay, perfect. Oh, now that worked. I'm like, why is it not fucking? Never mind. I got it now. Thank you. I appreciate it.
No problem.
It's been a long day. Okay.
Hey, Ryan.
Yeah.
Do you have a calendar link? Like I was looking at the Excel thing, says ask on Slack to make an appointment.
Yeah. I still have not made one. Partially by choice and partially because I keep forgetting. It's often just easier to send me a message on Slack and we can either meet then or figure something out. I tend to be pretty available like after 5 p.m. on weeknights. I know that's when classes, but so when I have one-on-ones with people, it usually ends up being like from 5 to 5:30, or it's like a weekend, or I mean, generally for probably until the new year, my schedule is going to be pretty open. So like send me a message on Slack. We can figure it out. If I can get a Calendly link made, I'll set that up. But it's one of those things where like the amount of effort it takes me to do it, it's like more than like a very quick task. So I always put it off and I just keep doing that and not doing it. And it's starting to become bad. I need to do it. So I will try to. If I don't have one in there though, seriously, just send me a message. Like we'll figure it out. I'm tend to be pretty available.
Heard. Thank you.
I will say that I think my choice of not having a Calendly link has meant that no one wants to have one-on-ones with me because I haven't actually had one yet. There's a lot of people have been like, I want to set up a one-on-one with you, and then I just don't hear anything. So I don't know if that's because like they want to talk to somebody else, or I'm fine with that if it's what it is, but or maybe the Calendly
It's the
link.
Calendarly link.
Okay, yeah,
Honestly, yeah. That's because we're kind of in condition. Hey, you want 1v1 Calendly? So it's like, whoa, no Calendly link. What?
okay.
Like, how are we gonna meet? How do you how are we gonna Zoom? But yeah,
Maybe I gotta bite the bullet then. Okay.
it's
Yeah.
just like I gotta
No,
bite the
not-
bullet and make an Indeed account.
Okay. Well, now that Careers in Code is done, for me at least, I can think again. So maybe I'll have some bandwidth.
Yeah,
now
because
that I know-
I'm telling you right now, when projects are, like close to being done or in the next 10 weeks, we will call you. Like we will literally Slack you and you're gonna get
Yeah.
very annoyed with us.
Yeah, you're gonna get annoyed. Like when we
I'm-
gotta start implementing our APIs, you're not gonna
No,
have
I'm-
a good time with
I'm fine with that. Like, I mean, I think you all know this, but like, I get paid for this, and like, I get like paid pretty well for it. So like, I'm fine with it, and it's fun. So like, reach out whenever you want.
Oh yeah, definitely. And we're definitely gonna reach out, especially once we start getting, our projects to the point where we need the APIs. But yeah, definitely. Because
Cool.
I don't know how I'm gonna do it. And
I'll
my
say, I
my
think you're doing
project-
better than you realize you're doing. I'll put
no,
that out
I'm
there.
really not. I really wish I can, like, I want a better grasp of things or of the concepts. And
Mhm.
like I said, for me, if I'm able to kind of explain it to someone, that's how I know I understand it, or I understand a lot of it. So, and I'm not there
Yeah.
especially with JavaScript.
Check out
JavaScript
the,
threw me all off. JavaScript threw me
Yeah.
all off. And so I'm trying to kind of play catch up on that, and then also play catch up on the homework, and study new things, new concepts, new languages, and also work on the capstone. So it's a little overwhelming, but other than that, I mean, it's gonna be okay.
The boot camp environment is like very difficult for this, and I haven't really had quite the experience you all are having. Like for me, like I figured all this stuff out over like the course of like 8 to 10 years of just like playing around gradually. So like for me, it was like very much like a slow process.
Yeah.
I don't know if I could do what you all are doing now. Like it's very overwhelming.
We are learning multiple languages and different concepts in different ways in less than 6 months.
Yeah, it's quite absurd.
Yeah.
But the other side to it is like, to some degree, that's kind of how the industry works. Like you do kind of get thrown in the fire on a lot of stuff. The thing that I will say though, that's at least for me made it better is like, as you start to get more of a broader foundation, you find weird parallels between like weird unrelated things. So it's like having like a broad foundation and understanding a lot of different things about a lot of different things. Like it means you can sort of learn things faster because you can be like, oh yeah, I heard about this, but in a different context over here. Okay, I can bring in that knowledge, and I know about that from over there, and I can bring in that knowledge. And it's not like you're starting from zero every time.
And
Yeah.
that's for me, that's why I'm looking forward to learning to another language, because I hear that once you're at least good enough in the concept of one language, a lot of that stuff transfers over to an extent.
Yeah.
So it's not like you're learning from, zero.
Yeah. I mean, I'll say if you want another language, I mean, yeah, I know you don't have time right now, but I'll put in my vote for the next language I think you should learn. I think you should learn Python next.
I'm going to have to anyways, because I'm going to back and stuff. So
I might be freezing myself.
you froze.
It's like you guys are taking turns on who's freezing and who's not.
I'm not sure, right? He's still frozen.
Yeah, I think
Okay.
Snyder, both you and I are both having some internet problems. And that compounded together is not a great situation.
I just said you guys are taking turns on who wants to freeze next.
Yeah. I just switched over to the other Wi-Fi network though, and hopefully that makes a difference.
You're saying something about Python?
Yeah, so I mean, I think it could be a good next language to learn because it's very similar to JavaScript in a lot of ways. Typically what makes new languages hard to learn in my experience is like not that they are completely different, it's that they have new types of concepts, like a few new ones. So you sort of have all the same stuff, and then you have like a new thing that's like a novel thing that language does. And then you sort of have to like figure that out and figure out how that sort of fits into everything else you're doing. I think what would make Python good is that it largely doesn't have that compared to JavaScript. It's more just like a different syntax with a similar concepts. And that means that like it would be a good next language to learn because I don't think it would be that difficult for you to learn. Does that make sense?
For sure. And that, like I said, that's also why I'm kind of looking forward to learn these other languages, just so I can make those connections.
Yeah, cool. Well, any other stuff, folks? I think otherwise I'm probably gonna head out here. I think I'm at my parents' house right now, and I think dinner might be ready pretty soon. That's I'm sort of in between Thanksgiving and Christmas, sort of camped out at my parents', and it's been really nice to have meals cooked for me every night. I'm like not used to that.
No, that's awesome. Enjoy it.
Thank you. Well,
Thank you for your time, Ryan.
yeah, for sure. And next week you're back to regularly scheduled programming with Max, but feel free to reach out if I can be of help at all. And have fun back with Max again.
All right. Thank you.
Yep. Bye.
Bye.